Hello everyone. Today I wanted to show you how to read data from an Allen Bradley PowerMonitor 5000 and plot the phasors to where you can actually see what the relationship between the voltage and current is for a three-phase system. This became pretty useful in troubleshooting the implementation of one of these devices if you don't yet have vector talk metrics, energy metrics installed. But this particular plot I've made here helped us to troubleshoot an inadvertent crossing of the CTs on a service to an industrial facility, and it really gives some goofy numbers when that happens. But anyway, here is a phasor plot for voltage of line 1 is in this dark blue, then voltage of 2 is in the red. It's about 120 degrees out. 3. And then the larger magnitude vectors are the current. So line 1 current is in yellow, and as you can see, its value is quite a bit larger than the voltage and just unitless numbers. It's about 1750 amps. And it's about the same for line 2 current, and then line 3 current is something similar. So this diagram here, this display is derived from the data coming directly out of an online PowerMonitor. One of these, each one of these cells is using DDE to connect directly to the PowerMonitor and bring the data into Excel, where I could then manipulate it down here to create my phasors. And if you look long enough at it, you'll see that they are changing in magnitude and angle slightly. Pretty consistent load, pretty uniform power. It's lined at neutral voltages here. It is a solidly grounded Y system, but I've got it for the voltage, the angle, and the magnitude. And I create my layout for what I'm going to use to develop each of the voltage phasors, and then the angle and current, so I can do the same and plot them out here in the real world, or in the plot, to show what's really going on. Make it easier than looking at some of these numbers, especially when you're looking, as I mentioned, to find a set of CTs or swapped set of CTs, any number of issues. But what we found when we powered this on, there was an issue with phase B CT and phase C CT and phase B CT being swapped. So when we did that, it's not quite the same as if you switch one leg of a three-phase motor, it reverses it. If you swapped two more legs, you now reverse it back the other way. When we had one CT's polarity swapped, or when we had these two swapped, we moved one down here and we moved the other one up here. Well, phase C, or line 3's voltage being here and its current being up here, as you can see, created a much larger angle. Should have been at the green line and where it was when it was swapped. And then the same with phase B, and then a really large angle, an obtuse angle actually, between phase B voltage and where phase B current was measuring when the CTs were incorrectly installed. We were getting normal numbers on phase A. We would get the correct kilowatts, the correct kVAR on that phase only. Phase B and C were not mirrors of each other, or just inverses or negatives and positives of the same number. They were really quite out of whack. And one thing that really allowed us to find this was to take a look at these phasors when we pulled the data in, and we saw, well, B and C were physically 120 degrees off of where they each should be. And once we found that, we moved it, power factor, we read normal. Some other parameters we looked at were the sequence current was actually reflective of what we would have expected on the positive sequence current, and that's because all of our voltage phasors were correct, and the rotation was A, B, C, which is actually kind of rotating counterclockwise or clockwise, which is opposite of convention. That's what the negative sequence current was, why it was being called negative, because the order of the voltage went A, B, C, and then the current went A in that same order, A, C, B. So it said, okay, you have 1700 amps in negative sequence current. And that's really what led us onto it. And then we found out, okay, hey, these were misappropriate or misapplied, misinstalled. So it's kind of a cool little tool. It's the same diagram we would see on one of our harmonic power quality analyzers. To do the same thing, we check our phasors, make sure we're close to spec. It's about 0.94 power factor, something like that. So that made it a little easier knowing this relationship. If you had a really awful power factor, you make it a larger angle, make it a little bit more difficult to discern if you had a really bad power factor. In this case, we were able to figure it out and got it working properly. Just in case you wanted to see how I was pulling this data in, as you can see up here in my formula bar, once I had already created a topic in RSLinx, I enter into the cell equals RSLinx, so it tells you what application to use, the OR bar or the bar, and then the topic name. This here, my topic is customer named, so I'm not showing you that. This is just where that topic name that you configure in RSLinx or whatever your OPC server would be if you were using something besides RSLinx. You'd put your topic there. It could be Bob's Manufacturing. Then you would do a exclamation point and then a single quote around the tag name. So this is a PowerMonitor 5000. It's tags, which is why I can use a name tag here instead of a file and a number, and tell it how many items you're going to bring back, which is and how you're going to present it is one cell and one column, which is just one cell. And that's what I did to these, which was voltage, phase 1, 2, 3, magnitude, current 1, 2, 3 magnitude, and then angles for both of them. You can really get a good picture of what's going on. So if you'd like to see more or see some more power troubleshooting tips or how we handle some things, feel free to reach out, like, subscribe, and I appreciate you watching. Thanks.